Okay, so today we are going to be finishing up SQL data definition language by talking about views, and then we are going to go into some theory for a week and be talking about the underlying theoretical basis for SQL's data manipulation language, and that is the relational algebra and calculus. So we'll get done with views, then we'll start the relational algebra later in today's lecture. Probably end up finishing the lecture on relational algebra sometime Thursday, and then also go over the calculus on Thursday. So we've already talked in general terms about views and their advantages and disadvantages. This lecture, we are concerned with how we actually create views in SQL. So the slides have these definitions for views, which we've already covered. They don't actually exist in the database. Instead, they're derived from base relations. And we'll see that they can be either dynamically generated via a query over the base relation, or they can be cached using a technique called view materialization. And you see that right there is the second term. View materialization means that we actually, after we have done the query on the base relations and gotten the table representing the view, we cache it. And we try to maintain that cache value as the underlying base relations are updated. And how we do that, we'll cover in a little bit. First, we want to cover the syntax you use to create SQL views, and also throw a little more terminology at you. So we've talked about views in general terms. There are two concepts, horizontal view and vertical view, that you should be aware of. So a horizontal view is one where you're filtering rows from a table. You're giving someone a restricted view to the tuples in the relation. In the example you see here, we are restricting the view to employees or staff who are in the branch whose ID is B003. So it might be that this is a view prepared for the branch manager of branch B003, and we don't want that manager viewing the details for other branches. So this is called a horizontal view, and it shows you the simple syntax you use to create an SQL view. So you start with create view rather than how do you create a table? Create table. And you give the view a name, and you can drop a view just like you can drop a table. And then you use the as keyword, and after that you have what is called the defining query. So this select star from staff where branch equals B003 is called the defining query. Okay, so I'll actually just write that down. So right here, this part of it, this is called the defining query. And you, whoa. Okay, it went way off the screen. Okay. Try to make it a little. I'm getting used to writing on this thing, and I have to actually look at the screen while I write, so it's a little awkward. So that's the defining query, and as you can see, it's written over one base relation, which is the staff base relation. So that's a horizontal view. Any questions about this rather simple view that we've created? And after you've created the view, you can display it just like you would a table. So you could say select star from manager 3 staff, and you would get the results as well. Okay, so that was a horizontal view. A vertical view is one where you might be showing all tuples in the relation, but now you're filtering out certain columns. For example, in that staff relation, salary might be considered a sensitive column. And so you might want to have a directory based on the staff relation, but you want to omit the salary field. So in this case, I've called this create view staff 3 because it's actually on the staff at branch 3. So it's kind of a vertical and horizontal view combined. And I might have called this staff 3 directory because perhaps that's what this view represents. And as you can see, my defining query has now listed the columns that I'm interested in, and it's omitting the salary attribute. So that is a vertical view. Okay. Now, in addition to that, oftentimes you want to create views that display aggregate information. So we have a horizontal view, a vertical view. Now we have views that display aggregated information. And you sometimes may also be drawing these views from multiple relations. So here we're creating a view that shows how many properties each staff member at each branch is managing, so a count. And again, now you're seeing a slightly different thing. Notice this was missing before, this comma-separated list in parentheses. This is naming the columns in the view. You don't give them types because the types are derived from the types of the corresponding columns in the defining query. So the number of columns here must match the number of columns in the defining query. And there's a direct one-to-one match. So s.branch number will appear as branch number in the view, and s.staff count will appear as staff count. Count star will show up as count in the view. So this is just a way of naming or renaming columns. And then in this case, we are performing a join between the staff and property for rent. We could have done a natural join if we had wanted, but I wrote it out explicitly. And we're grouping by the branch number and staff number. Okay, so pretty simple and straightforward. This is the general syntax. So you can see create view, view name, and then optionally you can rename the columns. Then the subselect is the defining query. And then this optional with check option has to do with updates. So you may be able to update a view by either changing the columns or deleting tuples or adding tuples. And the with check option says whether the SQL optimizer should check whether the tuple you're inserting actually meets the requirements of the defining query. So for example, coming back to this manager 3 staff view, if I tried to insert a tuple whose branch number is B006, that violates the defining query, right? B006 is not B003. So the with check option controls whether that insertion is legal. Obviously, it should be illegal. So I think in general, you want the with check option just because I don't see any point to being allowed to insert tuples that would be illegal according to the defining query. Okay, and this is just regurgitating what I've already told you, so I'll let you look through it on your own. So I got a question on Piazza about one of the homework questions, and I promised that it would be answered in class today. So to that individual, here's the answer to your Piazza question. The question on the homework assignment, number 2, is asking you to do something called view resolution, where the homework question is writing a query on a view. So instead of writing a query on base relations, it's actually writing the query on the view. And in order to actually execute that query, remember, it's possible that the view table has been stored in cache, but it's also possible that the view is being dynamically generated. If it's being dynamically generated, then we somehow have to map the query on the view into a query on the base relations, and that is called view resolution, the process of merging a query on a view with the defining query for the view. So it's a merge process. So the example we're working with is that we want to count or get a count of the number of properties managed by each staff member at branch B003. So our original query was this one right here, and it printed the counts for all branches. Okay, so the view we had, staff property count, gave us the property counts for each staff at all branches. Now we just want the property counts for the staff at branch B003. So you can see that instead of selecting from a base relation, we're selecting from this pre-existing view. And what we want to do with view resolution is map this to a query on the underlying base relations, which is something that you'll have to do for one of the homework 2 questions. So there's a procedure for doing this. You start with the column names in the select list, and you're going to translate them into their corresponding column names in the defining query. So here we were selecting staff number and count. And if you go back to look at the defining query, staff number maps to s.staff number, count maps to count stars. So the first thing that we do is we replace staff number and CNT with this thing. We say select s.staff number, and remember the as keyword in this case is renaming columns. So we are renaming the columns using from the base relations into the columns that we want to use in the view, in the result actually from that view. Then the view name is going to be replaced with the corresponding base relations from the defining query. So here we were selecting from staff property count, but that's a view. So now we go back to the defining query, and we see that the base relations were staff S and property for rent P. So we replace the from staff property count with from staff S and property for rent P. So now we've replaced the columns with the columns from the base relations, and we've replaced the the view name with the underlying base relations. Next, we have to tackle the query itself, the selection query. So how are we going to handle that? It turns out to be a merger. So what we're going to do is we're going to take the where clause from the query on the view, and we're going to AND it, Boolean AND, with the where clause from the defining query. So it's very simple. So the where from the user query is combined with the where from the defining query using an AND. So you just verbatim take both where clauses and connect them with an AND, which is what we've done here. Then the group by and the having clauses are copied from the defining query, and so is the order by. The group by and having clauses are copied from the defining query. The order by is copied from the view query. So here we are ordering by staff number, so that gets copied in verbatim for the order by. The group by and having was copied in from the defining query. And so when we're all done, we have this final query which is now completely mapped onto the base relations and onto the attributes from the base relations. So you're being asked to do a similar thing on homework 2, where you're being given in one of the problems a query on a view, and you're being asked to do view resolution, which means that the end result that you produce is a query on the underlying base relations. So is that clear what's going on? Okay. And when you hit this part of the homework assignment, you might consider referring back to these slides. I think there's something like slides 30, where are they, 40 through 42 in the notes. Okay. Now, second thing, I also got this on Piazza's. So one of the homework questions also, I think this is the same one, goes on to say that you want for each of the queries on the views given to indicate whether it's a valid or invalid query, and to do then query resolution on the ones that are valid. You don't have to worry about the ones that are invalid because supposedly you can't create a query because it's invalid. And the question from the student was essentially, I'm inferring now, they ran all the queries in MySQL and they all worked. However, just because they work in MySQL does not mean that they are valid according to the ISO standard, which is the defining standard for SQL. So when you answer the homework question, what I want to know is not does the query work in MySQL, I want to know whether that query is valid according to the ISO standard. Okay, well, if you're wondering where to find that information, perhaps you'll go to slide 43 of my notes because this is where I talk about it. So first of all, if any of the columns in the view is based on an aggregate operator, then you are not allowed to use that view or column in the where clause of a query on that view. So for example, I was the count field right here. This count field is an aggregate or aggregated column. So I can't use that count field in any query that I perform on the view. So for example, I can't say select star from staff property count where count is greater than 2 because, well, can someone tell me actually what if I did view resolution, what would count be replaced with? Come on, you just saw it. Count star. Okay, if you remember back to chapter 6 in the book, where we talked about the fact that the ISO standard says that you cannot use the aggregation operators in where clauses. So the reason that you can't use a column derived from an aggregation operator in a where clause on a view is because if you tried to do view resolution, you would end up with an illegal query on the underlying base relations. Now, you might run this in MySQL and it might work. Can anyone suggest a reason why it might work in MySQL? Say it louder. If it has stored it as a temporary table, then it's fine, right? If it's using what we call view materialization, and it's actually storing it as a cache table, there's no reason why this query shouldn't work. My guess, I haven't looked into it, but my guess is the reason why this query might be working in our version of MySQL is that the MySQL interpreter is using a materialized table, in which case this query isn't a problem. Okay? So same thing over here. This one may look okay. All we're trying to do now is count the number of tuples in the staff property count. And this would have been fine if I said select count star from staff property count. That would have actually given me the number of tuples in the view. But when I try to say select count on the count column, that's no good, because when I try to do view materialization, CNT gets replaced with count star, which is no good. So any query on the view cannot use a column derived from an aggregated operation. So in the homework assignment, if you see such a query, you should simply say it's invalid, and you don't need to do view resolution on it. But don't try to test the answer on MySQL, because it may go ahead and perform the query even though it's illegal according to the ISO standard. Okay, so here's a second restriction. There's only two restrictions on the queries that you can do on views. The second one is if it's a group view, i.e. you use the group by operator or anything that involves an aggregate function, you can't join that with a base table or another view. So our staff property count was a group view because we grouped by branch number and staff number, so we can't attempt to join this view with any other table or any other view. Now again, you try to do it in MySQL, it may well work, because if it's been materialized as a temporary table, it's all good. But according to the ISO standard, it's not good. It's not a legitimate operation. Okay, so anytime you have a grouped view, that is one that involves an aggregation operation, you can only perform what I would call simple single relation or single view queries on it. Okay, that's it. Two restrictions. But that's what that question is asking you about. Questions about that? Okay. So then, as I talked about at the beginning, we have a question of view updatability. So remember way back here we had the with check option, and that dealt with the updatability of the view. Okay, so there's two ways a view can be updated. One is the base relations change. You insert a tuple into the base relation. You delete a tuple. You update the tuple in the base relation. So anytime you update the tuple in the base relation, obviously the view should be updated. Okay? But you also may have the situation where you want to update the view rather than the underlying base relation. And the question is that legal? And the answer is it's legal if there is a way that the update can be unambiguously mapped back to the base relation, i.e. that if you modify the view, then you can figure out unambiguously how the base relation should be modified in order to be consistent with this update from the view. Okay, so let's give it a try. Let's say we try to insert into our staff property count view, the one that we counted the number of properties for each staff member. We want to insert into it a new tuple where staff member SG5 is managing 2 properties. And the question is, should that be a legal update? And the answer is no. And the reason is, try to map this update into the underlying base relations. Well, first of all, you're clearly going to have to add 2 tuples to the property for rent relation, because clearly the staff member is supposed to be managing 2 properties, but we haven't given any details about those properties. So there's no way we can unambiguously map this update back into an update on the property for rent relation. So this insert has to be denied. Okay, so we say it's not updatable. This is a non-valid update. Okay, let's say, okay, I'm going to be a little different. I'm going to create a view where I am going to be keeping track of all of the property numbers managed by every staff. So now I took out the aggregation operation. Okay, now it's a list of all properties that are being managed along with the staff numbers in the branches. Okay, so again, I'm going to, but all I'm including is the branch number, the staff number, and the property number. So again, I'm going to try to insert into this view a new property. Property PG19 managed by staff member SG5 at branch B003. Okay, well, to do that insert, what am I going to have to do to the property for rent relation? Do I need to insert a tuple into it? I'm inserting one here. Okay, here's a question. It looks like if I'm inserting a record here, it looks like I either need to insert a record into the staff relation or a record into the property for rent. Okay, how many people think we're going to insert a record into the staff relation? And how many think we're going to insert into property for rent? I love the, okay, so it's not clear. So this is a new property, okay? We're saying it's PG19 SG5. We're not adding a new staff member here. The staff member is presumably pre-existing. We're adding a new property. So the answer is, I think we can unambiguously, well, I'll take that back. The query optimizer isn't that bright. I can unambiguously know that I'm adding a property record and that the update would be to property for rent. However, property for rent has other columns that have to be included, that is, aren't optional, such as the amount for which it's going to be rented, the owner number, and that information is missing. So in fact, we are not allowed to make this insertion into the view because we cannot unambiguously add a new tuple to property for rent. And just a second, Thomas, I'll get to you. Actually, to the query optimizer, it may not even be clear whether it is the staff relation that should be updated or the property for rent relation that should be updated. And that may be what was giving you all some issues when I asked, that even you all were confused as to which it should be. So I was taking advantage of some semantic knowledge that I had. I knew pretty much that since I was adding a property and not, I knew what this was. I was listing properties, and therefore the meaning of this view was I was listing properties. Therefore, when I added a property to it, I knew I needed to update the property for rent relation. But I was taking advantage of semantic information that would not be available to the query optimizer. So it probably could not even figure out whether I needed to add a tuple to the staff relation or property for rent. In any event, it's ambiguous as to how I would update the base relation. So this again is an invalid query. Thomas. Maybe, but the question then is, can the query optimizer figure out that the insert has to go into property for rent?
Is that something you can tell it to do? Or?
No. Okay. It has to be something that it can figure out on its own. Okay. So you would probably try it and see if it worked, but I don't actually think it's smart enough to figure it out. Okay, so in fact the ISO standard gives us some guidelines as to when it is okay to update a view. First of all, you're not allowed to have the distinct keyword be in the query. So if the distinct keyword is in the defining query, you can't update the view. It makes sense because if distinct is in there, distinct must be eliminating multiple rows, right? So if we try to insert a row into the tuple, into the relation, into the view, that could potentially map into anywhere from 1 to gajillion tuples. Or if I try to update a value, but I use distinct, it may be how many tuples are we updating in the base relation? We don't know because we eliminated all but one of the tuples. So we don't know how many. Basically what we don't know is, given a row in the view, we don't know how many tuples it maps to in the underlying base relation because distinct got rid of them. Okay, let's see. So every element in the select list of the defining query is a column name. So what that means is that you can't use aggregation operations. This is a fancy way of saying you can't use aggregation operations because they are not column names. Count star is not a column name. You'll say, oh, but Brad, what if I say count star as staff count? Nope. The column name was count star. It was an aggregation. So essentially what it's saying is that every element in the select list of the defining query must be an actual column in the base relation. It can't be a derived column. Okay, same thing. You can't divide by 12. You say in the view, select monthly salary, or I'm sorry, select salary divided by 12 is monthly salary. You can't update the salary because the query optimizer doesn't do algebra. It can't reverse salary divided by 12 and realize that you need to multiply what you inserted by 12 to get the salary. Okay, it's not smart like that. So any basically two, and in fact I may rewrite that to be clear, any query, any defining query that involves a derived column, you can't update that view. Okay? 3 essentially says if you did a join to get the view, you can't update it. So Thomas, that kind of goes back to your question, which is I said probably the query optimizer still can't figure it out. Number 3 is essentially saying that. It's saying we don't trust the query optimizer to be able to figure out which relations need to be updated. Therefore, if the query was formed from a join, you can't update it. Okay, and number 4, same thing, kind of is close to number 2. It's really related to number 2. If you used a group by or having clause, the whole point of a group by or having clause is to organize things into sets, usually for the purpose of counting, which means that you really can't reverse it out. Just like when my original, basically this one right here where I tried to insert into staff property count to the fact that SG5 managed 2, this is a violation of 4. It was using a group by operation to count the number of properties managed by each staff. And I can't, if I basically insert into a tuple that's a summary, like this one is, I can't figure out, I'm going to have to generate multiple tuples to match this summary. I have no way of doing it. So that's what 4 is essentially saying, is anytime you've done grouping, you're not going to be able to reverse the operation. So it's illegal. Okay? This, I think, may be a homework question too, although I'm not exactly positive. So questions about this? I think it's pretty straightforward, common sense. Okay. I'm not going to worry a lot about migrating rows. So as base relations are updated, rows appear or disappear from views, and those are called migrating rows. Let's see, the big thing with migrating rows is actually when you're doing an insert into a view and it violates the defining query. Okay, if you specify with the with check option, that won't be allowed. And I already gave you an example where this was selecting all staff with in the B3 branch, and now we try to insert into that view a person in the B2 branch. That should be illegal because clearly it was only meant to be people in the B3 branch. In fact, we were hoping to restrict the manager from being able to see anyone else's details. So it also becomes a security issue. Okay, I'm not, like I said, I'm not really worried about this, so don't worry too much about it. We've already talked about the advantages and disadvantages of views, so we talked about that on the first day. I'll let you read through it. Last thing I want to say about views is this idea of caching. So dynamically recreating a view from scratch each time we ask to see the view can be time consuming, and so often the database system will cache the table returned from such a query. And that means it's fast to retrieve the table, but it also means the table becomes invalid anytime we update the underlying base relations. And rather than simply throwing away the table, which may have taken a lot of time to create, oftentimes the databases simply try to update the cached table. So how does it do that? Okay, you have to think about it a little. Okay, so here are some examples. View maintenance aims to apply only those changes necessary to keep the view current. So some changes to the underlying relation don't affect the view at all. So for example, I might be having a view that keeps track of our big dollar staff members. They're the ones who manage properties for more than 400 pounds. Woohoo! Okay, maybe not big dollar. Even in pounds, that's not a huge amount. But at any rate, we want to keep track of all staff members in branch 3 who are managing properties greater than 400 pounds. So it should be clear that anytime I insert a tuple whose rent is less than or equal to 400, that doesn't affect this relation, correct? Or this view. We good? Anything with a rent less than 400 obviously doesn't affect it. Okay? What happens if we insert a new property for staff number SG37 and the rent is 600 pounds? Do we care? No, why not? Because it's already there. Staff member SG37 is already there, and we are selecting distinct. So we don't, it's already there, and since it's distinct, we can't add it. Conversely, let's say we added a new property managed by SG50 for 600. Now, we do need to update the view because SG50 is not currently in here. Okay? So that's kind of easy. So the inserts are easy. The updates and the deletes, not so much. Let's say that we delete a staff member, SG37. Let's say we delete a property. So we're going to delete a property. Okay, so we delete property P05, and it was managed by SG37. Without looking at the book, should we delete SG37 from this view? Okay, property 5 was 600 pounds. You don't know, right? The question is there another property in the property for rent relation managed by SG37 that goes for more than 400 pounds? Not obvious, right? This is where it gets tougher. The query optimizer is now going to have to sort through the relation, see if there's another property managed by SG37 for more than 400 pounds. If there is one, then the view is unaltered. If there is not one, SG37 is deleted. We're not going to worry about how the query optimizer pulls off this task in this class. That's more of a graduate level exercise. But I just want to give you a taste of what view maintenance is all about. Basically, you have to be able, or the query optimizer has to be able to look at the defining query and determine, based on the tuple being added, deleted, or changed, whether that is going to end up modifying the view without hopefully having to rerun the entire query. Okay? Now, that said, if I asked you on a quiz or a test, I might give you these different scenarios that I just gave you. You should be able to tell me what needs to be done. I might say, I insert a new property, P05, managed by SG37 for 300 pounds. Does the view need to be updated? Answer, no. Okay? Or I might give you the relation, and I say we are deleting P05, managed by SG37, and you'll have to check now the relation to see if there's any other properties managed by SG37 for more than 400 pounds in order to answer the question. Okay? Good with that? Okay. Nice deep breath. Things we won't discuss. Well, we won't discuss. Okay. So that's it for SQL's data definition language. Okay? Take a little bit of a deep breath. We are going to be entering the theory zone, although I don't think it is all that intimidating, so I hope you don't get too intimidated by it. But what we're going to be talking about is not the relational calculus right now. I'm too far into these notes slides, sorry. We're going to spend the rest of today and Thursday talking about something called the relational algebra and relational calculus. First of all, calculus has nothing to do with the calculus that you saw with differential equations or with integration or derivatives. It's something completely different. It takes some getting used to, but it's not horrible. In fact, SQL is very much based on the relational calculus. Okay, so if you'll find that often if you can simply figure out how to map an SQL query in or a relational express something as an SQL query, you can often easily map it to the relational calculus. So the relational algebra and relational calculus form the theoretical basis for the query language, for relational databases query language, i.e. the DML or data manipulation language. So in chapter 4, it was the DDL. Chapter 5 is the DML, data manipulation language. And the relational calculus is actually the gold standard. So the relational calculus is actually the formal definition of the relational databases data manipulation language. It's not relational algebra, it's relational calculus. Okay? So relational calculus came first. Relational algebra came later and was meant more as a high-level procedural query language. So the relational calculus is a non-procedural or declarative language. The relational algebra is procedural, but at a high level. So in fact, every operation in the relational algebra maps into an operation in the relational calculus. But whenever you form a relational database and you create its query language, you say that the query language is relationally complete if every query that can be expressed in the relational calculus can also be expressed in your query language. So SQL is relationally complete because every query that can be expressed using the relational calculus can also be expressed using SQL. Okay, same thing. Any query that can be expressed using the relational calculus can be expressed using the relational algebra. We go through the relational algebra first because most students seem more comfortable with relational algebra. Okay, so the first thing to know about the relational algebra is that it is closed, meaning it works, all operations or operators in the relational algebra work on relations, and the result is a relation. So it's closed, meaning every operation will produce a relation. And the relational algebra does not do in-place updates. The relational algebra produces a new relation. So if you do an operation like set union, okay, so you do union relations A and B, it doesn't update either A or B. Instead, it creates an entirely new relation, C. So that's what the first point is. The second point is saying because you are creating relations, the results can be changed. So I could say A union B, and that result can then be chained, and I could say union with D. So you can chain operations just like you can chain operations in arithmetic, right? A plus B plus C, A plus B times C. Same thing in the relational algebra. So this is all pretty standard stuff, very similar to arithmetic. Okay, there are 5 basic operations in the relational algebra. Select, project, the Cartesian product, taking the union, and taking set difference. There are 3 additional operations that are added as complementary operations: join, set intersection, and set division. However, on a quiz, which you will see on Thursday, if you are asked what are the 5 basic operations, it's the 5 listed there. Technically, join, set division, and set intersection are not part of the relational algebra. Okay, they are syntactic sugar because they can be formed from combinations of those 5, and we'll show you how. So they are syntactic sugar. They are not part of the base set. Okay. And you should be pretty okay with the, oh good, it doesn't even show up well. It shows up well on my computer. Okay, so the blank rectangular box here on my computer shows up nicely as, so this is just trying to show you what the different operations, so select selects certain rows. Project selects, harder to do the vertical, selects columns. Cartesian product, every possible combination of the 2. It's like multiplication. So every possible combination. So A and 1, A2, A3, then B1, B2, B3. So every possible combination of the tuples from the 2 relations. Union adds together the tuples from the two relations. Intersection takes the common elements from the two relations. Set difference takes everything that's in R but not in S. So for example, if R was administrators and S was professors, R minus S would be all administrators who were not professors. Joins we've gone over. I don't think these slides are from the book. I don't think they're particularly good. So, but no, they're not particularly good. However, I guess I'd go through them. So here's T and U. This is a symbol for a join. It looks like a little bow tie. And it does we'll see that there's different types of joins. In this case, it's an equijoin. So it's being done on the common column. As you can see, it eliminates one of the two common columns. This right here with the single half of the bow tie is called a semi-join. So sometimes you only care about the tuples in one of the two relations. So you do a join on both relations, but the result is only the tuples from the first relation. So here we join T with U, but in the result, we only care about the rows that were in T. So for example, we might want to know about which branches have properties assigned to them. So we might take the join of properties or branches with properties, but all we care about in the result is the branches. So any branch that matches a property in the property relation would appear in the result, and that's called a semi-join. We've talked about outer joins. In an outer join, in this case a left outer join, all the tuples from the left relation appear in the result, even if they don't match a column, or a row in the right relation. And any tuple in the left relation that does not match will have nulls for the corresponding columns in the right relation. Okay. I think set division, until I finally figured it out about 4 years after I started using SQL, is completely confusing. So don't even try to figure it out from this diagram. Here's the meaning of set division intuitively. We have a relation of national parks, of visits to national parks, like Brad went to Yellowstone, Brad went to Yosemite, Brad went to Glacier, Tim went to Glacier, Nancy went to Yosemite. And we do a query where we want to say, I want the set of people who have visited all the national parks. Okay, so we want all the people who have visited all national parks. The set division is looking for something, for the set of something that has done everything. Okay, another example would be in our hotel schema, we want the set of people who have stayed at all rooms in the Grosvenor Hotel. So set division is saying, give us all the so-called, we'll say, people who have done everything. Okay? So the way that shakes out here is that we are dividing S into R, and, well, actually we're dividing W into V. So here's W. So we want everyone who's done both activities 1 and activity 2. Well, if you look over here, A has done both activities 1 and activity 2. B has done both activities 1 and activity 2, but C has only done activity 1. So in our result, we want A and B because they are the two that have done all of the activities in W. Does that make sense? Yes. I've never seen a good reason. I can kind of tell you that the idea is the remainder here the remainder would be C1, is it's kind of like you have your set of people who are full. Like when you do 7 divided by 3, 2 is the full number, and then 0.33 is the remainder. So I guess that's kind of the idea, is that set division returns the full, people who've done everything. And then the remainder is people who've done a little bit, but not everything. That's my best explanation, because I've actually never seen why it was actually called set division. To me, that's the one that makes sense. Other questions about set division? Okay. Now, I'm going to blow through the next slides because these all match things that you have already seen. Okay? You just have to get used to using the fancy Greek letters, which means you have to just study the slides. So, if you want to do selection, it looks like this O with a tag at the end of it, and then you have the predicate at the bottom. So for example, salary greater than 10,000 with the staff relation in parentheses. So you can see the relation goes in parentheses, the little O with the tag on it is the selection operator, and then with your ands and ors, you're supposed to use fancy mathematical stuff. So the and is that, and the or is that, rather than saying and or. So those are the fancy symbols for and or. And I'm fine with you using this for not. Okay, here's projection. It's the uppercase pi, Greek letter for pi, then a column separated list of columns and the relation. So here we're asking for these 4 columns from the staff relation. Okay. Union, pretty intuitive. It's the union symbol that you see from one of your math courses. And again, there's this notion of union compatibility right here that you should remember. Union compatible means that you have to have the same number of columns in each of the 2 relations, and that each matching pair of columns have to have the same domain type. They don't have to have the same names, just the same domain type. So union compatible means 2 relations have the same number of columns, and for each matching pair of columns, the same domain type. Okay, and again, union, here we are unioning our, we're taking the union, we're finding all cities where we have either a branch or a property for rent, and the 2 relations actually are not union compatible initially because they have the same number of columns, but they actually had the same domain types too, but it wasn't quite what we were after. So because ID and property ID are not really the same, so we actually project down and just ask for the city from each of the 2 relations and then do the union, and that makes them union compatible. Set difference, again, the big minus sign, you should have seen that in your classes. And again, here we're finding our deadbeat branches, so we're finding all branches that are located in cities where the branches don't actually manage any properties. We probably want to either shut them down or tell them to get on the stick. Okay, now intersection is our first bonus operator. So it's not part of the actual basic 5. Instead, it is built on top of them. So the operator is the intersection, but you can get this one from set difference. Okay, so the way you get it from set difference is you start, you're doing R intersect S, you take R, Okay, so R is this right here, this white plus the blue, that's R. Then we're going to find everything that's in R but not in S, which is right there. Okay, so at the top in blue, that's everything that's in R but not in S. And finally, we subtract whatever is in R but not S from R, which must give us whatever is common to R and S. I know that sounds backwards and not easy to interpret, which is why they give us intersect as a complementary operation. It's just not real natural to try to write intersection this way. But if you think it through, it does work. You're just subtracting whatever is not common to R and S, that's what R minus S is, from R. Therefore, once you've subtracted out whatever is not common, you have whatever is common. Okay, that doesn't make sense, memorize it. Yes, Thomas?
The white space is the one selected,
Right, the white space is the intersection. So that is the intersection, the white space. In fact, probably, so actually I probably will add an arrow, make that clear. I'm not going to do it now, but I'll do it afterwards. Right, but the fact that you asked means it's not 100% obvious, so I will. Okay, so that's another pretty obvious example. Cartesian product is a big X, so you denote it as RXS. And you simply take the, there's no dropping of common columns here, so everything shows up. Notice that the ID columns here, I know these are different actually. This is for student ID and this is for course, but the general idea is you don't drop common columns from the result. They all go into the result. So you end up with all the columns from the first relation and all the columns from the second relation and all possible combinations of them, which of course gets unwieldy very quickly when you have even like 100 tuples in both relations. You're already up to 10,000. And now this is actually, so here's an example of a join. So a join is actually a selection on a Cartesian product. So we are crossing, what we're doing is finding all students. We're finding the courses taken by each student. So we're doing a join of student with courses, and the way we do that, we take the Cartesian product, and then from that Cartesian product, we only take those tuples where the student's ID matches the course's ID. So in this case, going back, student ID 1 took 140 and 255, student 2 took CS 302. When we did the Cartesian product, you'll see that student 1 ends up being included with student 2 who took CS 302, but in fact, student 1 did not take 302. So when we now impose this equality constraint that the student ID equal the course ID, only the ones highlighted in red end up being put into our final selection. So student 1 took CS 140 and 255, student 2 took CS 302. So rather than writing it all out like this, because this is kind of complicated to look at, they introduced join, and it is written using, the bow tie. You can have trouble finding it in your character sets. I'll go back, it's somewhere, it might be in the symbol character set if you're trying to do it for the homework. And LaTeX has and HTML both have. HTML has an entity code for it. LaTeX has a way of getting it too. So Joins are notoriously difficult to implement efficiently in relational database systems, which is why it took them so long to actually come into widespread commercial use. It was over 10 years before, once they were developed in the research lab, to where they really started moving into commercial use, and it was because joins are hard to implement efficiently. Just taking a Cartesian product creates potentially millions of tuples in a real database, so you don't actually want to take the Cartesian product. So theoretically, there are various forms of joins. So there's the theta join, equijoin, natural join, outer join, and semi-join. The most general version is the theta join, and this F down here can be any relational operator. In practice, we only care about equals. It's the only one we ever care about, but this is the theory, so you should know that in its most general form, a join could be we could say for student ID greater than course.id, or for student ID not equal to course ID. In many cases, these are nonsensical predicates, which is why we usually only use equal. But the most general version of a join is called the theta join. We only, and you can rewrite the theta join as a Cartesian product and a selection using that predicate. Now, in practice, we only care about the equijoin. So the equijoin is a theta join. It's just using the equal sign. So when I know that the terminology gets confusing, someone might say, well, what's the difference between an equijoin and a theta join? Nothing. An equijoin is a theta join. It's using the equal sign. Okay? So you already know this is an example where we are taking the student and ID and listing all the comments they've had about classes. So we were doing a join on the course ID and the comment, and everything in the join is the union of these two projection operations. So in the result, we have ID, name, course ID, and comment. So it's the, and you drop the common column, which is ID. There they didn't. But generally in a join you do. So generally in a join, you would drop the common column, so you wouldn't see ID twice. Okay, natural join is an equijoin where you don't explicitly indicate the columns. So in an equijoin, you explicitly indicate the columns that are part of the join. And a natural join is an equijoin. It's simply one where you're doing the join over the common columns and you don't specify them. So notice there's no predicate here. Before, in the equijoin, notice there was a predicate. Here, there's no predicate. When you omit the predicate, it's a natural join. Okay. Then the outer join, both tie, except notice there's missing the left part. So this is a left outer join. I find this confusing. I would think that I associate missing bar with omission and the having a bar with inclusion. So I always get this wrong because I always think that this is a right outer join, because I would think that the inclusion here says that we want everything in S, but that would be incorrect. Common sense does not rule here. So in fact, it is the missing one where all the tuples are included. So this is saying we are doing a left outer join, so all tuples in R will be in the result. Okay? I would love to ask a mathematician why, because I do think this is counterintuitive. But this is a left outer join, and if I wanted a right outer join, then I would omit the right side of it. Okay, so this is a left outer join. In fact, I don't even think the book makes an effort to do a full outer join, because then it's going to look like a gnarly X. Okay, there's going to be a couple it's not quite the Cartesian product because it's going to have little footers on both sides for a full join, full outer join. And finally, we have the semi-join. Okay, this makes a little more sense. We don't care about S, we only care about R. So what this is saying is we're doing a join of R with S, but in the result, only tuples from R will be present. So we're taking, in the result, any tuple from R that matches a tuple in S. So you can write it this way as a full, shouldn't say full, as a equijoin, or in this case a theta join between R and S, but then the projection is over the attributes in R. So when you see projection over A, that means a projection over the attributes in R. Okay, so that's a semi-join. And let's do a quick review and stop there then. Okay, so quick review. Theta join, top of the hierarchy. So if we are trying to, I'll let you go, but I think this diagram might help. So let me just quickly draw the diagram. Okay, so theta join, top of the list. Okay, so here's our theta join. Okay, then we can have an equijoin and a natural join is an even simpler form of a equijoin. Okay, and then we can also have a semi-join. Actually, a semi-join can be a theta join, so I'll take, that was bad. Whoops. Erase that. A semi-join is actually another form of a theta join. So that's a semi-join. Okay, and then also as part of a equijoin, you could have an inner join. Well, how to do this? Okay, so that's one thing. Then I'm going to do one other thing. So then you can kind of also have an equijoin. And it can be either an inner join or it can be an outer join. And if you have an outer join, it can be a left, a right, or a full join. Okay, so that's kind of a taxonomy of joins to help you with the terminology. Okay, and under this you can have an inner join or an outer join could be a natural join. That's why I had to draw this separately. An inner join or an outer join is allowed to be a natural join. Okay, so again, no quiz today, but there'll be a quiz on Thursday covering both today and Thursday's material. On Thursday, we'll finish up with the relational algebra and then get into the relational calculus.